Laparoscopic surgery is a minimally invasive surgical intervention that uses a laparoscope and other instruments inserted through small incisions in the abdomen. But training new surgeons is a bottleneck. The traditional one-to-one training model, where one expert trains one trainee, does not scale, and this problem is especially critical in resource-limited areas, which face a severe shortage of surgeons. Our goal is to tackle this by designing a low-cost, high-fidelity haptic simulator to accelerate training and skill assessment. To ensure our robot meets the demands of real surgery, we took a data-driven design approach. We recorded expert surgeons performing a cholecystectomy on simulated and explanted real organs using optical tracker and force sensors. As you can see in this video, we then used that motion data to define the kinematic and dynamic requirements for our device. By analyzing this data, we extracted key matrices like tool velocities and the required device workspace. This allowed us to translate real-world surgical actions into concrete engineering specifications for our robot, such as requiring an end effector stiffness of over 15 newtons per millimeter and a workspace diameter of about 170 millimeters. Using the information we extracted from the collected data, our initial concept was a cable-driven robot, which promised a compact and lightweight design. However, we foresaw significant challenges with low stiffness and complex calibration, which would have compromised the haptic fidelity. These limitations led us to pivot to a more robust architecture. Our final design is a rigid link dual 5-bar parallel robot. This architecture provides the high stiffness and isotropic workspace crucial for realistic haptics. As the plot shows, the device's workspace fully encompasses the expert surgeon's motion data. Additionally, through optimized design for manufacturing and by introducing more 3D printed parts into the device, we reduced the cost from nearly $20,000 for previous prototypes to under $5,000 for the final version. To the right, we see an expert surgeon demonstrating the workspace of the device. A key feature for every haptic device is force feedback. Commercial sensors are prohibitively expensive. To meet our low-cost objective, we needed to develop a custom 6 degrees of freedom force torque sensor. Our initial design is a magnetic Hall effect sensor, which relies on detecting the change in the magnetic field due to the displacement of the magnets under forces. While very low cost, this initial design had limitations in accuracy under high forces and fabrication difficulties. We then evolved the design to a piezoelectric-based sensor, which provides much higher accuracy and reliability, giving us the high-fidelity force feedback we needed for effective training. The system operates under two modes. On the left is active mode, where the robot provides assistive control and haptic guidance. We can see it enforcing virtual walls and guiding the user along a path through an assistive control law called virtual fixtures. And on the video below, we see the robot constraining the tool's pivot point through an assistive control law known as remote center of motion. On the right is passive mode for skill assessment. Here, an expert surgeon is performing cholecystectomy on an explanted organ, and the robot is completely backdrivable, allowing us to record their motion and forces using the custom-designed force sensors for objective analysis.